Hello, my greetings to everyone. Hope you are safe and sound during this pandemic. This particular lecture, it covers fundamental insights into wire arc additive manufacturing, its recent advancements, the present challenges, and the industrial outcomes. So myself, V. Chakravarti, I am with the Department of Materials and Metallurgy, National Institute of Technology, Trichy. Anyhow, I'm not going to waste my time in advertising my institution, so let me quickly step into what are the classifications of metal arc metallurgy manufacturing. So this additive manufacturing, it is just an umbrella term. So and particularly this metal additive manufacturing is like broadly diversified into two types. So one is powder-based additive manufacturing, and the other one is wire arc additive manufacturing. So this powder-based additive manufacturing, it is concerned, the name itself indicates that the powder is being used. So we can see here a powder will be like spreaded over the table, and a laser or any electron beam power source will be like focused into those powders, and wherever the area of the powder that is getting exposed to this laser power source, so those areas will be like melted and it will get solidified to get an exact component. So here you can observe that for making a very small component, how much powder is practically needed. Okay, so this is how a powder additive manufacturing that generally works. So here out of all these areas, only very few areas are exposed to this laser. So only those areas whichever is exposed to laser, those particular areas will get melted and it will get solidified, and the remaining all the areas will stay unaffected by heat, but however the nearby zones we can observe, so it may lead to like a partial melting of powders, so which may cause some agglomerations, which we cannot rework with that unfused powder. Okay, that becomes a potential threat. Okay, so here we go. So we can see what is wire arc additive manufacturing. So the name itself indicates that this wire arc means the wire is going to be melted to form any complex geometry or any complex contour. Okay, so here this is how a setup it exactly looks. So here we need a workbench, then a substrate will be there. Generally, whatever the materials we are going to deposit, the same material we will be generally using as a substrate. For example, if you are going to deposit stainless steel 316L, then the same material should be chosen as the substrate material. Then we can use any welding power source such as gas tungsten arc welding, or else metal inert gas welding, or else we can even go for plasma arc welding, or even we can go for some hybrid techniques like combination of two or more welding techniques. Even that could be possible. And especially while metal deposition, we need to protect the environment, okay, without like getting chemical contamination. Especially the oxide layer will be interacting with the molten pool, which may lead to some oxide film formation. So this could be like potentially avoided by usage of the shielding gases, which will be creating an inert gas environment. And generally we use argon, or else we can even go for helium, or we can even go for some varieties of gases such as argon plus nitrogen or argon plus CO2, or else we can even go for argon plus hydrogen. So that is based on the requirement we generally plan. And this kind of wire feeder we can even do externally in case of TIG welding, or else if it is a CMT or MIG welding, then generally the wire will be like integrated into the starch, and this wire will be directly melted without any external power source such as this tungsten rod. And here we will be having a computer to control and monitor the feedback mechanisms, that either the starch is moving as per the programming coordinates or not. Okay, so this is a general thing about this wire arc additive manufacturing, and especially while building a component, when we should be like certain about in what axis we are going to build, either in X direction or Y direction or Z direction. So generally single wall components we generally build in Z direction, so it means that towards this height we will be like building this component. Okay, so here we can see the experimental layout. like how exactly and wire arc additive manufacturing setup it exactly looks. So here we can see cold metal transfer based additive manufacturing. That welding machine is interfaced with the robot. This robotic arm, it could potentially move in all degrees of freedom. And here we can observe some base plate attachment will be there. So these base plates are clamped with this kind of like fixtures, so that it can avoid thermal distortion. So that will be covering in upcoming slides. So here we can see a magnified image of how the table that exactly looks. So in this table we'll be fixing a base plate and we'll be clamping use of this kind of fixture, and this wire will be like coming through this wire feeder, and directly it will be like deposited over here. So here the table is, this workbench is completely fixed one, where it cannot move or rotate. But however, this work table is like flexible enough to rotate in all directions. So which is one of the most advantageous one. So which will minimize robotic movement. Okay, even so this so-called 6-axis wire arc additive manufacturing setup. And in case if you are like dealing with some tough materials like titanium or magnesium copper or magnesium aluminum, if you are dealing with such kind of sensitive materials, then obviously we have to go for this kind of a closed chamber, where this chamber will be like completely filled with argon gas or even helium gas at a very high pressure, so that there won't be any possibility of interacting any outside gases, especially during the time of deposition. So of course we won't be facing any kind of like oxide layer formation, especially at the time of deposition. And here are the path planning. Okay, how a robot is supposed to move in, what are the parts that it should travel. Okay, so each and every path planning strategies that will impact much on grain refinement. Even this path planning, it will impact on the geometrical fidelity, and even what are the heating and the cooling rates of the component. That the solidification rate is like completely dependent upon what is the tool path planning. Tool path planning in the sense in what part this robotic arm is supposed to move. Okay, so there are different patterns out there. Either we can go for a raster pattern, which is nothing like continuously. It will be like it will be depositing without any gap. Even we can go for a zigzag pattern. Okay, so zigzag pattern is like more efficient, and even we can go for this kind of variable contouring, spiral, and even continuous pattern, that is also possible. And even few other patterns also I have shown, this hybrid pattern, matte and adaptive matte. So even these patterns are available. So other than these kind of patterns, one of the most interesting things about this wire arc additive manufacturing is nothing but the weaving motion. Okay, so here we can see what is a weaving motion. So here you can observe that this torch is like slightly, it is like it is moving right to left, left to right. Likewise, the consistent movement could be easily observed. Okay, so especially whenever we are making this kind of like a weaving motion, which will eventually cause like a whirlpool stirring. So this whirlpool stirring, which will result in fine grain formation. Okay, so here we can observe that EBSD pattern. This is the electron backscatter diffraction, which will typically show that in which orientation the grains are oriented. So here you can see like a very coarser grains that are oriented in some particular direction. So these grains are like oriented in this particular direction, and these grains are oriented here in this particular direction. So there are no other directions, okay, which is like which is quite evident over here. But whereas whenever we are going for this kind of like arc oscillation technique, that which I have shown in this video, you can observe that a fine grained refinement can be possible. So which is just nothing like a whirlpool stirring. Okay, so whenever you are stirring this molten pool, then automatically the grains, it will get collapsed, and it will be like finely refined grains, and it won't be in one particular texture. Okay, so that is one of the advantages feature of this well pooled stirring. Then then the next thing we can see, what are the common differences between this powder based additive and wire arc additive. So in powder based additive we can see that the cost of the powder is initially very high, and there are some aspect ratios that what should be the specific diameter of the powder, and in what shape this powder is supposed to be. Either it is supposed to be spherical or any other regular shape, that matters a lot. And as we know that this powder means this kind of porosity will be one of the most common lattice tissue. So but whereas when we compare with the wire arc additive manufacturing, we generally never bother about any kind of like a grain size or anything else. So generally we will whatever the material we want to deposit, we can even go for any simple material, okay, like stainless steel 316L or inconel. Anything is available in form of a wire. Okay, typically we can melt those wires to deposit a component. So the material wastage is very, very minimum. Here we have observed that a very large quantity of powder will be like spreaded over here for just building a very small component, even though your component may be small or big, because however you just need to like stack this much amount of powders over here. But whereas in wire arc additive manufacturing you no need to have that much a huge material, so even a minimal material is like more sufficient for making a component. Okay, so the material wastage will be very, very minimum with the wire arc, so which we generally call it as a buy to fly ratio, because most of the aeronautical components are very costly. Say for an example, this titanium 6Al4V alloy, so which is like a very expensive material. Even a small quantity of material wastage, that matters a lot. Okay, so buy to fly ratio in the sense what is the actual component weight and how much material is being wasted to produce this much weight of component. For example, if you are producing 2 kg, the actual weight of the component is 2 kg, so you would be wasting like 5 kg of powders to produce 2 kg of component. Okay, so that is the fly ratio, means 5 kg which was 3 kg which was wasted, and buy ratio in the sense what is the actual weight of the component, which is nothing like the 2 kg. Okay, so the another most important thing we have to know that is this powder based additive manufacturing setup is like quite expensive. Say for an example, if we need a very simple setup, we have to expend minimum 1 crore in Indian currency. And if you are like interested in building a wire arc additive manufacturing technique, so hardly we have to expend like 50 lakhs or within 60 lakhs. We can even go for a very good very good 6-axis robotic machines. That could be possible. And what is one of the main important thing is like this wire arc additive manufacturing that setup is like a multi-purpose one. For example, if you are having a plasma arc, okay, so this plasma arc, it could be used for making a keyhole welding. Even we can do welding process by using this plasma arc. We can even do metal cutting. Okay, even metal could be cut very efficiently. Even the same plasma, or using the same plasma arc, we can even deposit the metal. Okay, so and we can perform this additive manufacturing. So which is like a multi-purpose machine. But this powder-based additive, it cannot be called as a multi-purpose machine. But however, this wire arc additive manufacturing setup, it is a multi-purpose machine. Okay, so which could be used like based on the application. We can plan like what process it is supposed to do. Either it is going to perform welding, or else it is going to perform metal cutting, or else it is going to perform wire arc additive manufacturing. So it is a multi-purpose machine in general, you can say. But however, as like this powder-based additive manufacturing, this wire arc additive manufacturing, it also has some serious problems like humping, stepping effect, missile layer formation, and few others are also addressed, and which could be seen in the upcoming slides. Okay, so let me quickly step into the common differences between a conventional casting and the wire arc additive manufacturing. In conventional casting, what we generally do, the step 1, we will create a pattern. The step 2, we will be creating a mold cavity. Step 3, we will be pouring a molten metal into the mold cavity and we will be allowing it to solidify. Once it gets solidified, we will break the mold and we will be getting the actual component. So this actual component will be like further machined and it will be further polished so that it will be meeting the industrial requirements. This is how a conventional casting it generally happens. Okay, but whereas here this wire arc additive manufacturing is something very different. Okay, so in casting we will be having a static heat. Okay, this heat is not a moving heat, which is otherwise called as transient heat. Okay, so here in casting it is a static heat. Okay, but whereas in wire arc additive manufacturing it is a transient heat, because especially while depositing from one end to the other end. Okay, so my metal is depositing from one end to the other end. So when the torch is traveling in this part, so this area will be like getting solidified. Okay, and this area will be experiencing a moving heat. Okay, so which is otherwise called as a transient heat. So the solidification rates are a little bit faster as compared to the conventional casting techniques. Okay, so here the step 1, we have to plan the robotic path planning. And once we have planned the part, and once we have set up all the x coordinate, y coordinate and z coordinates, then we'll be depositing a component, which is nothing but step 2. And step 3, we'll be like removing the unwanted components, because this component is having a lot of undulations. So these undulations should be removed. Sometimes most of the components that could be used in as printed condition, but few components may have like a very stringent industrial requirement to pass through the qualification. So in certain circumstances it could be like even undergo this kind of like machining process. So either we can even machine by means of any drilling or milling tool, or else we can even go for this wire cut EDM, which is one of the most conventionally used techniques. Which is one of the most often used techniques, especially to machine these wire arc additive components. Even that could be possible to attain a high geometrical fidelity of a component like this. Okay, so and there is no step 4, it is just that simple. Okay, and here I have just mentioned some few of the allowances. So in casting we will be considering a lot of allowances into practice, and we will be like producing a very big pattern. Okay, so we will be considering draft allowance, taper allowance, distortion, shrinkage and machining and so on. Okay, but whereas this wire arc additive manufacturing, we won't be worrying about a lot of allowances. Only shrinkage allowances and machining allowances will be taking place. The shrinkage allowance, it is mainly due to the dilution effects. I'll be covering about the dilution in the upcoming slides. And machining allowances in the sense as we can observe that the wire arc additive components, it is having a lot of surface undulations, which is having a lot of peaks and valleys. The surface is not very smooth enough. It is having a lot of undulated surfaces. Okay, so this kind of undulations could be potentially removed by means of this kind of machining process. Okay, about allowances, only these 2 allowances are generally considered for wire arc additive manufactured component. Okay, so here we can see the overview of WAAM. So generally we need a charge, which is nothing but a tick charge, and this wire was externally feeded. Even we can feed a single wire or double wire in tandem. So it is up to us. For example, if we are going for a bimetal deposition, we can use 2 different wires. For example, if you want to increase the deposition efficiency, the same material, the same wire itself we can use, but 2 wires at a time we can use using the same power source. Okay, so even that could be possible. Then the next step is like we'll be building a component like this. Okay, then after once we have built this component, then we'll be doing machining as we have shown here. Okay, so before we are doing all this process, so what is the first step we are supposed to do? First, we are supposed to do the simulation. Okay, before we are building an actual component, we have to simulate like how could be the heat source will be moving on. Okay, so what is the possibility of like evacuating the heat from the actual component? So it is nothing but the substrate, or which is otherwise called as base plate, which is like blue in color here. Okay, so generally whenever the metal is being deposited, the component will undergo high coefficient of thermal expansion and thermal contraction, so which will lead to building of residual stress complication. Okay, so whenever the material is being melted, so during melting the material will experience high coefficient of thermal expansion, and during solidification the metal will experience a thermal contraction. Okay, so repeated melting and solidification will be like taking place. So there will be a formation of like thermal induced stresses in the base plate, which may lead to this kind of base plate distortion. Okay, this base plate distortion is the most common problem, but however this could be avoided by using our base plate, which is like slightly thick enough, like minimum 15 to 20 mm thick. If you're using that kind of very thick base plate, this kind of base plate distortion could be greatly avoided. Okay, because the plate, it will be initially at the room temperature 32 degrees C, and suddenly if it is like exposed to a very high heat like 1600 degrees C or 2000, then obviously this base plate it could not withstand that high thermal shock, which will lead to the onsetting of residual stress complication, which may lead to this kind of plate distortion. So once the plate is getting distorted, so obviously all the coordinates x, y axis, whichever we have fixed prior before deposition, so everything that gets altered, so it would end up with this kind of like a failure component, so which we never needed. So if we need to work on this, we have to choose a base plate which is slightly thick, and I already told you that if we are going to deposit stainless steel 316L, the same material only should be chosen as the base plate. We cannot choose aluminium, or we cannot choose some other irrelevant material as a base plate. The same material should be used so that we can avoid the chemical contamination. Okay. So here we can observe that we cannot, after doing simulations, we have to do the pilot experiments. Okay. So using this pilot experiment, like we can plan like how to optimize the wire feed speed, how to optimize the current, and what should be the applied voltage, and in what should be the torch traveling speed. So each and everything should be like well optimized by manually or through any kind of programming techniques. So now prior to that, what we generally do is we generally do 3D slicing. Okay, well, 3D slicing in the sense the exact geometry would be like sliced into small segments, and those kind of slicing, after doing that kind of slicing, we'll be like we'll be doing a molding process. Then after that we'll be like we'll be coming up with a simulation, and after doing that kind of simulation, if that exactly works, then we will go for pilot experiments. And during this kind of pilot experiments, we may end up with this kind of like spatters and even irregular deposition. So each and every time of this kind of pilot experiments, we'll be optimizing all the process parameters. So once all the process parameters are well optimized, then of course we'll be getting a very fine component with a very high geometrical fidelity like this. Okay, so once we have fabricated this kind of component, it would be like machined very smoothly to attain this kind of like a glossy surface. So okay, so on seeing the surface, we cannot blindly conclude that okay, this wire additive manufacturing doesn't work. We should not jump into that kind of conclusion. Okay, so this kind of component, after machining, it will be looking like just like a brand new one. Okay, so for doing this, we have to optimize what should be the molten pool flow dynamics. Okay, that is one of the most essential one we should plan prior to deposition. Okay, so as I mentioned over here, after doing a lot of pilot experiments, we'll be optimizing the process parameters. In case of normal MIG, like a conventional MIG process, we will be like optimizing the process parameters each and everything manually. But whereas this cold metal transfer welding, which is nothing but a modified form of MIG welding process, so which was developed by Furnace Technology. So this kind of technique, which will be like offering more versatility, especially for wire additive manufacturing and also welding. So what is the main salient feature of this cold metal transfer welding is each and every process parameters are synergistic in nature. For example, if I am changing the wire's feed speed, then automatically the voltage, current, and all the other decisive factors will be changed can be changed accordingly. Okay, if I am changing one process parameter, the other decisive process parameters also will be changing accordingly. Say for an example, here the molten droplet will be like detaching from the wire. Okay, so that magnified image that was shown here, that which will be like detaching due to the pinch effect. Okay, so I'll be showing a small video clipping. Okay, so here you can see this wire is connected with the negative terminal, so it will be like detaching a droplet because avalanche flow of free electrons will be coming out from the wire, which will result in like a molten pool formation. Okay, so for each and every microsecond, this molten droplet will be detached from this wire. Okay, which could be like easily seen, and each and every time this polarity is getting changed from positive to negative and negative to positive. So I'll be like letting you to know what is the actual reason for this kind of pulsing effect. Okay. So in cold metal transfer welding, this pulsing will be more efficient, unlike other welding techniques. Okay, so which we generally call it as like variable polarity, like straight polarity and reverse polarity at a time we can make it out. Okay, and so in terms of like welding charge, just imagine this is a CMT charge, and this is a wire, and this is a base plate. Okay, say for an example, if this wire is connected with the positive terminal and the workpiece is connected with the negative terminal, and if I'm going to make a deposition, then automatically what will happen? This workpiece will be having some few oxide layers which I could not potentially remove through the wire brush. Okay, if I'm removing through the wire brush, then it may lead to some kind of like scratches or some undulated surfaces, which it doesn't like to happen. I like to remove all these oxide layers in an atomic level. So what I'll be doing, I'll be connecting it with the reverse. I'll be connecting this workpiece with the negative terminal. Wherever I have connected my I have connected anything with the negative terminal, the free electrons it will try to jump out. Okay, so this free electron, generally oxide layer, it will be deposited on the top of the surface. This free electrons want to jump outside, but this oxide layer will be creating a hindrance. So what will happen? Hammering effect will be taking place. So just consider this oxide layer. Free electrons will be like giving a hammering effect, and it will try to jump out from the surface of the metal, that which will lead to the removal of oxide layer. Okay, so everything that happens in microseconds, okay, which we generally call it as pulsing. So in one half of the cycle, this kind of like right now deposition is made, and right now oxide layer removal is taking place. Okay, so whenever the workpiece is connected with a negative, then oxide layer removal will be taking place, and whenever the electrode is negative, then metallic deposition will be taking place. So for every microsecond, one half of the wave will be like metal deposition, and another half of the wave will be like oxide layer removal. So two things will be parallelly occurring at a time. Okay, so which we generally call it as pulsing. So this CMT, this cold metal transfer welding, it has an very special feature which is called as pulsed advanced mode. Okay, using this pulsed advanced mode, you can come up with a you can avoid porosity, and also you can even deposit like a spatter-free material, and also you'll be like removing the oxide layers, especially at the time of deposition itself. Okay, so that is another advantage of the process. So here we can see what are the key decisive factors of wire arc additive manufacturing. Okay, so the first thing we have to worry about, what is the wire feed speed. Okay, so how much should we have to fix? In case of cold metal transfer welding, if once we fix the wire feed speed, then all the other decisive factors will be like fixed accordingly. But whereas in case of other techniques like plasma or MIG or any other techniques, we have to fix each and every process parameter. We have to customize each and everything on our own by doing any kind of manual optimization or any kind of like well-developed optimization techniques. Okay, so wire feed speed. Then the second most important one is the shielding gas flow rate. Then the third one is the torch angle. Okay, this shielding gas flow rate is very, very important, because if you are using a shielding gas of very less flow rate, then of course this would not be sufficient enough to shield the molten pool. So obviously the weld puddle will result in oxide layer formation. Okay, so if it is more sensitive metal like aluminum or titanium, then obviously shielding gas, which is very very important. So the metal will have like a decolorization. Okay, the metal color will get changed into like a chocolate brown. Especially it indicates that an oxide layer has been formed already. If for each and every time we cannot simply remove by means of a wire bridge, which is like a very very time consuming. Okay, so generally we have to give a very high flow rate, just like 20 liters per minute. Okay, so in that kind of a high shielding flow rate, we generally go for that. Then torch angle. Why torch angle? That matters a lot. Okay, this torch angle will be the key decisive factor for attaining specific texture. For example, if you are like if you are taking a material which is like face center cubic metal, say for an example stainless steel 316L, okay, and we are like so concerned to produce a component in a preferential texture. Okay, so in one particular texture all the grain should be oriented, then of course we have to give importance for torch angle. For each and every torch angle, the texture will be like keep on getting altered. For example, 15-degree torch angle, it will be having some specific texture. If it is like torch is getting tilted to 30-degree, it will be the end component will be resulting in different texture component. Okay, because the grain growth will be different. The grain can grow in straightward or sideward or even in angular ways or even in some other angle. Okay, so it is completely based on the torch angle. All these things, I mean, this kind of preferential building texture that could be possible. Okay, which is a hot spot of the research at present. Okay, then the next important thing is the arc oscillation frequency. Already I have talked about the weaving motion. Okay, so in what frequency this weaving motion is supposed to happen? This weaving motion which will be causing a weld pool stirring effect. Okay, so that's why this arc oscillation frequency is one of the concerned parameters. Okay, so generally we go for 5 Hz, 6 Hz or 8 or even 10. We generally go for that. Generally this arc initiation voltage, so that is very very important. For example, if you are going for the first pass, then we generally give a very high voltage, because especially the first bead should properly anchor with the base metal. If we are not giving very high voltage, then eventually after developing 3 or 4 layers, this first layer will get peeled out from the base plate. Okay, so which will be causing a lot of mess. Okay, so that's why initially we will be giving a very high arc voltage, so that the dilution will be taking place with the base metal, which will be causing an anchoring effect for developing the subsequent layers. Okay, so this arc voltage is one of the most concerned parameters. Then the current, pulse frequency. So in what rate we want oxide removal should be taking place, in what rate we want the metallic deposition should be taking place. So we will be planning everything by means of like pulse frequency. Okay, then the robotic path planning strategies also is there. As I told you that there are different robotic path planning strategies. So we can go for a raster pattern or a continuous pattern, or even we can go for like various kind of contours, zigzag pattern and so on. Okay, so then the next one is the most important one, is the interpass layer temperature. Okay, most of the lectures they would never ever addressed what is the importance of this interpass layer temperature. Okay, this interpass layer temperature is in the sense, first layer I am depositing, and how much dwell time I am going to take for deposit the second layer. Okay, so after depositing the second layer, how much dwell time I am going to take for depositing the third layer. So that dwell time, which is otherwise known as this interpass layer temperature. So how much time I am allowing my material to solidify. Okay, so initially my metal will be in red hot condition, and especially when it is in red hot condition, if I am depositing my material as it is, then which would end up with a lot of geometrical irregularities. So to avoid that, we have to maintain the interpass layer temperature. Like for every 200 degrees Celsius, for every 200 degrees C, I'll be like depositing one layer. Okay, so I'll be waiting until the layer gets cooled down to 200, and after once this layer has reached 200, then the subsequent layer will be deposited, and we'll be waiting until the next layer to get cooled down. Okay, and so which is otherwise called as the interpass layer temperature. Generally we go for 200 degrees C, or we generally go for 250 or maximum 300. Okay, for attaining a very high geometrical fidelity. And then the most important thing is the loading conditions for interpass rolling. So this is another important segment which we'll be covering in the upcoming slides. So especially whenever we have deposited a component, and if that components if that layer, okay, if that layer okay, so if that layer is having a lot of thermal heat, and which is supposed to be removed, so then we can go for this kind of interpass rolling, okay, which will be like a very high rolling load will be applied. So I'll be showing that later on. Okay, then the another one is the heat treatment temperature. So generally wire additive components, it never ever require heat treatment, but maybe in some worse circumstances, whenever we are using TIG or plasma process, the temperature would be rather high, which may onset this kind of residual stress formation. Okay, so in certain circumstances maybe heat treatment might be required. So if we are going to make a heat treatment, then we should be aware about what should be the specific temperature and what should be the specific duration we are supposed to do heat treatment. For example, stainless steel 316L, we generally go for 660 degrees Celsius, 660 degrees C for 6 hours. Okay, in case of like aluminium, it would be rather different. Okay, so heat treatment temperature should be the one of the most concerned one. And the machining technique. So in what technique we are going to machine, which is nothing like post processing. Okay, either we are going to machine using wire cut TTM or any conventional drilling or milling operation. Okay, so machining technique is also one of the key decisive factors in attaining a very high geometrical parts. Okay, so here I have like mentioned what kind of shielding gases we generally employ. Okay, either we can go for pure helium, or else we can go for argon. Either we can go for argon hydrogen mixture, or else we can go for argon nitrogen. So these three are like generally classified as metal active gases, because hydrogen, nitrogen and CO2 are like most active gases as we ever heard. Okay, so hydrogen, okay, how much hydrogen we can use? Generally we can go for 1 to 5% of hydrogen along with argon. Argon will be 95% and hydrogen will be like within the range of like 1 to 5. Okay, then nitrogen also would be in the same level, and even CO2 also in the same level. So what is the use of hydrogen? So especially whenever we are using hydrogen, especially for stainless steel, or else even whenever we are going for this kind of inconal solenoid, then obviously the lattice phase formation is one of the most potential threats, which we will be covering in the upcoming slides. So that could be like greatly avoided when we are using this kind of argon hydrogen mixture. And this argon nitrogen, what is the use of argon nitrogen in the sense, especially when we are using austenitic steels? Okay, austenite phase is a very unstable phase, so obviously austenite may convert into ferrite. So we may be using a lot of austenite stabilizers such as like chromium. This chromium is one of the very good austenite stabilizer, or nickel. Okay, so in certain circumstances, especially nickel is a very strong austenite stabilizer. Okay, as compared to the nickel, this nitrogen will be giving more than 10 times better austenite stabilization. Okay, so austenite phase is one of the most ductile phase, which is more preferable for obtaining a very high corrosion resistance and also very high ductility. We generally go for austenitic phase. Okay, austenitic phase, it should be more. Then only the material will be more ductile. If it has a lot of ferritic phase, then obviously the material will turn more brittle. Okay, so stainless steel, when it is being melted, it will be having some austenite and also ferrite. Both will be there. So at elevated temperature, it will be like purely austenite, and especially when the temperature is coming down, some few austenite will get converted into ferrite. So in order to stabilize the austenitic phase in getting converted into ferrite, we need some kind of like external influence, which is otherwise called as for that particular purpose we generally use nitrogen. Okay, nitrogen is a very strong austenite stabilizer, and it can improve the corrosion resistance to a great extent as compared to the chromium. Okay, so this nitrogen, whenever we are using, so it may form nitrocarbates, so which is
which can prevent the chromium carbide formation in stainless steel, and which can prevent the sensitization effect, because this carbon is one of the most potential element, which is like a very fine atomic radius. So that's why it can easily occupy all the interstitial voids and spaces. So that's why we cannot remove carbon, especially from any stainless steel. Even we can call it as low carbon stainless steel, but we cannot call it as the carbonless stainless steel. Okay, obviously carbon will be present because of the low atomic radius. Okay,
so this carbon, it is a highly reactive material which will be like reacting with the chromium, or else it will be reacting with molybdenum, and it will form chromium carbide or molybdenum carbide. Okay, so let's see here. So here you can see the metallographic structure. Okay, so especially in scanning electron microscope, we can observe each and every single grain boundary. Okay, this is a grain boundary you can observe, which is nothing like outer area. Okay, so inside this is a grain, and which is the outer one is a grain boundary. So especially during solidification, whenever the solidification is like very sluggish. Okay, so as compared to the powder additive manufacturing, this wire arc additive manufacturing solidification is very sluggish. Okay, say for an example, if you are like if you are considering any powder based additive solidification rate, it will be in the range of like 10 power 6 Kelvin per second, 10 power 6 or 10 power 5, because that very high heating and cooling rates will be taking place. But whereas in wire arc it will be like quite sluggish. Okay, so hardly 100 Kelvin per second, 500 Kelvin per second, not more than that. Okay, so during such circumstances, this grain will become more coarsen, and especially when it is becoming more coarsen, then what will generally happen? So just imagine chromium is there all over the grain. Okay, so some few quantity of chromium will be leached, and this kind of chromium will be like forming a globule, and it will be like reacting with the carbon, and it will form chromium carbide. Okay, this chromium carbide is an unwanted element which will potentially cause a lot of deleterious effects. Okay, such as like embrittlement. Okay, your material will turn brittle, and wherever this chromium carbide formation is there, it will be acting like a crack nucleation site. So from this chromium carbide, crack can easily penetrate. Okay, so that's why we generally avoid chromium carbide formation, so which is popularly called the sensitization problem. Okay, so if we want to potentially avoid this kind of chromium carbide formation, then we have to use certain shielding gases like argon nitrogen. So whenever we are using argon nitrogen, this nitrogen will be reacting with the carbon, because the reacting temperature is like very high. So nitrogen will be reacting with carbon, and it will be forming nitrocarbides. So once the nitrocarbides are formed, then obviously what will happen? So there won't be any free carbon left to form this kind of chromium carbide. So obviously when the chromium is very high in your stainless steel, then obviously it will turn more corrosion resistance. Okay, so obviously you won't be facing this kind of sensitization issue. So in order to work on that, the shielding gases is one of the most concerned one. Okay, even you can go for CO2, but not for TIG process, because this thoriated tungsten rod, which will be having a very high thermionic emission. So when it is reacting with the argon plus CO2, because CO2 is like a metal active gas, which will react with this tungsten, and it will start leaching out tungsten rod, and which will cause tungsten inclusions in your workpiece. So the TIG rod life cycle will be very less if we are using argon CO2 mixture. So generally it is not recommended. So for normal MIG welding or MAG welding, we generally go for this, but for TIG welding, we never use argon CO2 mixture. Okay, other than that, we can go for argon nitrogen for TIG, even we can go for argon hydrogen for TIG, but not for CO2. Okay, argon CO2 we never use for plasma, and also for this pure TIG process. Okay, here we can observe this kind of like lattice formation. So this lattice formation, which is nothing like a hard niobium shell, inside the, which is like a irregular L-shaped shell. So inside this shell, a lot of potential minerals are like entrapped inside. Okay, like molybdenum, chromium, and even few other materials are like entrapped inside this hard martensite shell. So obviously it will lead to demineralization, okay, so which may cause like a easy corrosion attack. Okay, so this could be avoided by increasing the cooling rates of the material. Okay, so if you want to increase the cooling rate, then either we can pour liquid nitrogen, especially in the molten metal, so that the metal will get rapidly solidified, or else we can pass externally some air so that these wire arc additive components can be easily solidified, especially by faster heat dissipation. Okay. So these are some of the post-processing techniques. So generally after deposition we will be removing the material. So machining is one of the most important post-processing. Then here mostly we never go for any kind of heat treatment, especially with wire arc components. But however, if we are like going for very high heat input, there may be chances of like residual stress formation. So which may be due to the building of very high thermal gradient. So in certain circumstances we generally go for a hot isostatic pressing, but this hot isostatic pressing is like restricted to wire arc, because most of the articles they have mentioned that there is no appreciable effects on hot isostatic pressing with wire arc additive components, but however this is like more effective with powder based additive components. Okay, then the other one most important thing is the short peening. So in this short peening technique, an ultrasonic transducer will be there, which will be hitting the workpiece, which is nothing like hammering effect. So obviously due to the short peening effect, a lot of the open porosities that will get closed. So automatically a lot of compressive residual stresses would be building up in the component, which is more favorable for tribological application and even for corrosion resistant application as well. Okay. Then the other important thing is a heat treatment. So heat treatment generally we carry out in the furnace, okay, to certain temperatures, so which is also one of the post-processing techniques, so which we often do to remove the residual stresses present in the component. Okay. In this slide I have addressed some present challenges in WAAM and what are the simple techniques to avoid that. Okay, I have mentioned some useful tips for the beginners. Okay, this humping is one of the most common problem. So this humping it generally occurs because when a molten metal is in red hot condition. Okay, at this kind of red hot condition we have to wait until it reaches back to the normal color. Okay, until then we should be like patient enough. But especially when it is in molten condition like this, or in red hot condition, we are depositing a subsequent layer, then it will lead to this kind of humping effect formation. Okay, so if we want to avoid, then we can go for either interpass layer temperature should be maintained, or else in case if we couldn't properly maintain the interpass layer temperature, either you can go for zigzag deposition. For example, zigzag means the first layer will be deposited, after that the second layer will be deposited just like this. Okay, so there won't be any continuous deposition will be taking place. Okay, so in a zigzag manner we'll be like depositing. So if we are depositing in that way, this kind of humping could be greatly avoided. And even we could see this kind of like mixer layer formation, we couldn't identify that which layer it corresponds to. So all the layers that are like sandwiched, and it is just like looking clumsy. Okay, so it is mainly due to the excessive heat input. Okay, we have to reduce the heat input so that this kind of like dilution effects could be greatly avoided. And stepping effect, it is also one of the most common problem. Like one layer and the other layer will be like merging with each other. So which could be avoided by using a CMT pulsed mode. Okay, especially in double CMT process we can overcome this, but in case of pure MIG it is not practically possible. And in pure MIG, what is the most commonly addressed issue is this kind of like spatter. The spatter will be everywhere. Okay, so which would end up with spatter. But whereas this CMT process, it is also one of the modified form of MIG welding, but however it is one of the most clean techniques. Okay, so it is like a very spatter free, and the dilution rates are very minimal, because it will be melting the metal at the least temperature, so the dilution rates are very minimum. So in the upcoming slide we will see what is dilution. Okay, so dilution means first layer I am depositing. When I am depositing the second layer, when the heat input is very high, the second layer will slightly impinge to the first layer, which is called as dilution. It will be looking just like a Venn diagram. Okay, so in this diluted area we can observe some kind of coarser grain formation, okay, which I have mentioned over here. So this kind of coarser grain, which is nothing like a columnar dendrites. Okay, so I have shown that kind of dilution region in optical micrography as well. So this is a dilution area. In this particular dilution area we can observe that grain coarsening can be more possible, that which will lead to failure. Okay, so mostly these are the potential sites for crack nucleation. Okay, so in order to work on that, we generally go for rolling operation. Okay, for at the end of each layer deposition, we generally go for rolling operation. Okay, so that I have mentioned over here. Wait. Okay, so I will show you that. Okay, so either we can go for rolling operation, or else even we can go for like a small coating of any kind of like materials like niobium, or else we can use a grain refiner such as titanium. Even such kind of powders could be like coated by means of a paintbrush or something else at the end of each layer deposition, so that this kind of like grain coarsening could be greatly avoided in the dilution zone. Okay, because this titanium is a very strong grain refiner, which will increase the surface wettability and which will promote the solidification rates, which will catalyze that. Okay, so generally we go for niobium or titanium nitride. So this kind of like potential grain refiners we can use. We can simply coat that potential grain refiners, especially at the end of each layer deposition. Okay, so after the end of each layer deposition, this titanium nitride is coated, and again this deposition is made. So especially at the interface area, we will be having a fine grains. Okay, so here I have shown what are the various grain structures are available. Okay, so most of the metal, all it falls under these four categories. Okay, either it could be planar, cellular dendrite, columnar dendrite, and equiaxed dendrite. Okay, so or else it could be like pure planar, cellular, columnar, and equiaxed. Okay, so generally it falls under these four categories. Or sometimes this dendrite formation might be unavoidable. Okay, so it is like completely based on like what is the thermal gradient to the growth ratio. Based on that only we will be deciding that what kind of grain morphology we will be getting. For example, if the cooling rate is very high, then we will be getting an equiaxed structure. This is how an equiaxed structure it typically looks. For example, if my cooling rate is very sluggish, then it would end up with a planar structure. Okay, then if it is like quietly intermediate, okay, then we will be getting like a cellular dendrite, a columnar dendrite. Okay, columnar dendrite is the most common structure which we can observe with aluminum, stainless steel, inconel. Mostly this columnar dendrite will be formed, and also equiaxed structure also that could be possible. Okay, so I will show you exactly how an equiaxed structure will look. So here you can see now. So this is how an equiaxed structure it will be looking. Okay, so columnar dendrites it will be appearing in this way. Here in this diagram you can see now. So some columnar dendrites are there. Okay, so this is how a cellular morphology that will be looking, cellular morphology. Okay, so here you can see now the cellular morphology. Okay, so this is how a typical microstructure it exactly looks. Okay, so here you can observe the equiaxed structure. Here you can observe the columnar dendrites. Okay, and the cellular structure we can observe over here. So it is like based on the heating and the cooling rates. So based on the thermal gradient to the growth ratio. Growth ratio means this is nothing but the grain growth velocity. Okay, based on these two phenomena, we will be getting a variable grain structure. Okay, so initially this is how solidification just generally happens. So in general, when a molten metal is like getting solidified, okay, so here you can see some small grains that are formed. Then later Okay, then later this green area, it represents that it is a molten metal. This molten metal will be like slightly solidified, and this grain will try to grow, especially wherever the heat dissipation rates are very high. Towards that particular direction, all the grains will try to grow. Okay, so grains will try to, as you can see that every plant, okay, every plant will try to grow towards the sunlight. Okay, in that particular direction, if the sunlight is in 30-degree incline, then plants will grow in this particular direction. If the sunlight is straight, then your plant also will grow in a straight line. Just very similar to that, these grains are. Okay, so wherever the heat dissipation rates are very high, in that particular direction, your grain will try to grow. Okay, so it's up to you, like in what particular direction you are planning your grain to be grown. Okay, so in that particular direction, you have to cool your sample in a very rapid way, so that in the fastest heat dissipation direction, these grains will try to grow. Okay, so that's one of the most important things I would like to touch upon. And here you can observe that especially in this kind of like a normal casting process, you can see that, okay, in die casting process, so this is a die. In the die, okay, the heat dissipation rates are very faster. So due to this, okay, so here the solidification will be more rapid. So the solidification will begin from here. So here you can observe some small finer grains, here some coarser grains, and here some equiaxate structure. And this orange area, it represents that some semi-molten state material is there. Okay, so this region we generally call it as a mushy zone. Okay, this orange area which we generally call it as a mushy zone. Okay, so which will eventually it will get solidified. Okay, so this is how a microstructure it generally looks. Okay, and here you can see some kind of like a micro cracks. Okay, so whenever you are having a sufficient interdendritic liquid, okay, this mushy zone, in this mushy zone some semi-solid liquid will be there. So that particular liquid will be so called as an interdendritic liquid. Okay, that particular interdendritic liquid, if it is sufficient, then it will heal all these cracks and voids, whatever, wherever these cracks happen, it will go and heal. So generally, if we are using aluminium, okay, we generally go for like a aluminium silicon wire, especially to weld aluminium. Why? What is the reason? Means the silicon will reduce the melting point of aluminium and it will improve the surface wettability. So the surface wettability will result in more interdendritic liquid formation. When there is more interdendritic liquid, then it will potentially heal all these cracks and voids very effectively. So that's why we generally go for aluminium silicon wire, like ER4043 wire. ER, it represents the electrode wire, and 4043, which is nothing but aluminium 4043 series, which is so called as a universal filler wire. For welding any grades of aluminium, we generally go for ER4043 because it is having aluminium silicon combination, which will improve the surface wettability. So the interdendritic liquid will be very high, so it can potentially heal all the cracks and voids. So if your material is having insufficient interdendritic liquid, this orange zone, then obviously it may lead to this kind of like a cracking formation. Okay, so if you want to avoid that, then obviously we need more surface wettability. So we can generally go for titanium. Titanium will improve the surface wettability. Titanium nitride will improve the surface wettability. And also even we can go for niobium, which will improve the surface wettability. Okay, we can go for such kind of potential heterogeneous nucleates as grain definers. Okay, so how to predict the cooling rates in wire arc additive manufacturing components? So that is one of the important hot topics. Okay, so by means of secondary generated arm spacing. Okay, so as I have told you about what are the various grain structures like columnar, dendrite, planar, cellular. Okay, so mostly this columnar dendrite structure will be generally present. So in this columnar dendrite structure, okay, so this this region we generally call it as a primary arm, and this small humping we generally call it as a secondary arm. Okay, this first humping, second humping, third humping, we call it as a secondary arm. This straight path we generally call it as primary arm, and these are the sub branches are called as secondary arm. Okay, so if the spacing is like very high, okay, if the spacing is very high, it means that the arm spacing is very high, means
the solidification rates are very sluggish, because your grains are overgrown. So that's why the arm spacing is very high. So if the arm spacing is very congested, okay, say for an example 10 micrometer, 5 micrometer, if the arm spacing is in that particular range, it means that your grains are very fine in size, okay. So based on the secondary tended arm spacing, we generally say that how far the solidification rates are, okay. Just for a knowledge, I just included this slide, and here we can observe that how far this grain refinement could be possible especially at the interface. Here you can observe this kind of like a very coarser grains, okay, especially at the interfacial region. Over here the interfacial region is there. So in the interfacial region, coarser grains are developed. So whenever we are using this kind of like a niobium coating or something else at the end of each layer deposition, so you can avoid this kind of like a coarsening effect. So here you can observe at the interface, you can observe a fine grain configuration that could be observed, okay, especially at the interface area. So this is the interface. In the interface also coarser grain only is there without titanium powder. So after depositing each and every layer, if you are depositing this titanium layer, then obviously the interfacial zone will be having a fine refined grains, okay. That is one of the key advantageous features. Okay, so this titanium is one of the most potential grain refiner, as I told you earlier. So it is pure aluminium. If you are adding few quantity, just like 1% or 2% of titanium, then all the coarser grains are getting refined into a finer grain. If you are using titanium nitride, which has very strong potential heterogeneous nucleate, okay, which can refine very fine grain, okay. So that could be possible. Either we can use this kind of grain refiners, or else we can go for this kind of rolling operation, which I was supposed to discuss earlier, okay, but this slide was it came a little bit late, okay. So this rolling operation, after the end of each deposition, will be performing this kind of rolling operation by applying a very high rolling pressure like 80 Newton, 80 kilonewton, 100 kilonewton, 200 kilonewton. Likewise, we will be applying a very high rolling pressure, so that you without any kind of grain refiners, this kind of like grain refinement can be possible. So especially during cold rolling operation, so the coarser grains will get crushed, okay, and it will be like forming a very fine grain structure. However, one of the most important thing is this roller will be like dissipating the heat, especially from the deposited area. So faster heat dissipation could be possible, and even an intermetallic, coarser intermetallic could be like broken into like finer fragments. Even that could be also even possible, and even grain refinement could be also made. But one of the most important things which we should consider is we are giving excessive rolling load, which will lead to tearing of layers, okay. So only optimal rolling load should be applied, okay. So that is that should be given more significance, okay. Then the other things are like you can make either single wall additive, or else even you can go for multi-wall additive. So single wall additive means only one single layer will be there. So even though this component is very big, only one single layer is there, okay. Over one single layer, multiple layers are deposited. So this kind of like a multi-wall additive means, so multiple layers will be deposited over here. So here a lot of spatters can be seen. So these are one of the most commonly addressed problems, especially in MIG deposition, okay, metal inert gas deposition. So here we have shown like to improve the deposition efficiency, you can use this kind of like two different wires in tandem, so that deposition efficiency could be increased. Or else if we are like interested in depositing a bimetal, like this would be titanium and this one would be nickel, even these two can be deposited at a time by using a common heating source like TIG source, okay. And so even this kind of bimetals could be deposited. So here are some of the potential applications. Here you can see
like stainless steel, bronze. Okay, these two metals are deposited. Here you can see copper with aluminium. Even you can see this inconel 625 with the stainless steel 316L. Even this kind of like different metals that could be deposited. Okay, then one of the most important one which we should be knowing is the mechanical anisotropy. Mechanical anisotropy, in the sense, anisotropy is a common term. Okay, so it means that change in any property that with respect to the direction. Okay, so which we generally call it as anisotropy. So especially if we are like taking a biopsy of a sample, especially in this particular direction. Okay, in this particular direction, if I am taking a biopsy, so obviously the tensile strength would be rather poor as compared to the tensile specimens in this particular direction. Okay, because in this particular direction, because each and every layer is deposited in this particular direction. So along the deposition direction, whenever we are taking a sample, so obviously the tensile strength would be rather very high. So the ductility will be very high. But whereas when we are taking in this kind of transverse direction, okay, this is a transverse direction and this is a longitudinal direction, and in this transverse direction the tensile strength would be rather poor, but not too much. So this kind of things are called as mechanical anisotropy. Why this mechanical anisotropy that generally persists means because whenever we are depositing, okay, so this area will be having one kind of grain morphology, this particular area will be having another grain morphology, and the bottommost area will be having a very different grain morphology. So that's what I have shown here. So it is just nothing like a front view image. Okay, so in the front view we can see that the top layers are having dendritic morphology with secondary dendrite arms, the central area which is having columnar dendrites, and the bottommost area which has like cellular grains without any secondary dendrite arms. Okay, so every area different grain morphologies are there, means in every area the micro hardness that varies, tensile strength also that varies. Equiaxial morphology means it will be having highest micro hardness as compared to the other grain morphologies. Okay, so here different grain morphologies are there. So variable mechanical property, so variable corrosion resistant property also as well, and variable micro hardness and other things. Okay, so that is generally based on like what kind of grain morphology we have obtained. Okay, so generally we will be getting a mixed structure, not everywhere the same equiaxial or everywhere the same columnar dendrite. So everywhere it will be like different grain morphology, which will result in this kind of mechanical anisotropy. So if we want to overcome this, then we have to play with the deposition strategy. So either we can go for different deposition strategy, like we can plan like a zigzag pattern, or we can plan a raster pattern, or we can even plan adaptive mat. So different planning we can make, so that this kind of like coarser grain formation could be greatly avoided. We can obtain a homogeneous grain structure. Okay, so in order to attain that, we have to play with the path planning strategies. Okay, so here I have shown different bimetals. Okay, stainless steel 316L and low carbon steel. These two metals are deposited over here. So it is nothing like a bimetallic interface. So even this kind of like one or two materials could be like deposited with each other, which we generally call it as bimetals. And here we can see some few of the applications of WAAM. So you can see engine block. Okay, so it is like once after deposition, and this is after doing proper machining. Okay, and this one also, it could be possible like an IC engine. Okay, that engine block, it could be potentially made, and even this kind of like propellers, especially for rowing the boat. Okay, so we need some propellers. Even that kind of propeller blades could be done. Okay, here we can observe, and these are nothing like a biomimicking surfaces, which are like a kind of like a scaffolds. Okay, for like a tissue regeneration, or else to improve the osseointegration property of the bone, or to improve the bionic function of the bone joining formation. We can generally go for this kind of like biomimicking surfaces, now especially for fabricating an implant. Even this could be possible with wire arc additive manufacturing, but still it is in research level only.
not it is like in in a commercial way. It is not going on. Okay. Then here we can see some few other applications as well. Okay. Here quickly let me rush up due to the kind of time constraint. Even we can fabricate this kind of like overhanging structures or something like this. Okay. So these are the potential applications of wire arc additive manufacturing. So this one is one of the propellers which we use in the boat. Okay, for steering and rowing the boat, we generally use this. Okay, thank you, and I would like to convey my deepest thanks and gratitude to my guide, Dr. S. Jerome, faculty of MME department, NIT Trichy. Thank you.